Hello, 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 hello. Welcome back. We are back in business. So, Ege, can you please try to talk? Can they hear you? Let's try it.
Hello guys, can you hear me? Please, if you can, please just write it
Yep,
in the chat.
it will be perfect. Let me introduce today's topic. Since we have mock exam for Bilkent Erzurum Laboratory School tomorrow, we will be going through one paper one example. It might be two as well, but we will be focusing on today 2017 HL paper one. Okay, they can hear you. Everybody can hear you. So again, shall we start?
Yeah, let's start.
Let's go. So this is the paper one. Okay, so the first question is about what is the sum of coefficients when the equation is balanced with the whole numbers. So since this was upon a request, we are planning to give you 15 to 30 seconds per question so that you may write your answers on the chat and we can see how it's going so that you will not be bored as well. And yes, Mert, he said it's going to be a majority of paper one questions. So we can take the answers for the first question about the coefficient balancing. Ege, do we have an answer, by the way?
Yeah, of course.
I'm sure you do.
Yeah, it's easy, and I think our viewers will do this.
I also feel in the same way. Let's remind our followers that the longest chain usually has a coefficient of 1. So they do not really need to do that. This is going to be multiplied at the ends. Maybe I'm giving too much clues, but still it's okay. Do we have any answers?
Also, it is saying whole numbers.
Yeah,
so
whole numbers.
You can eliminate a.
Please be careful about this word. Please be careful. This is a DP style. So if you do not have any answers, maybe we can go on with that, right?
Yeah, let's do it.
Okay, let's start with the carbons. So carbon is here 8. So let's write 8 here directly. And for the hydrogens, we can see that this has to be 9. So 9 times 2 would be 18. And let's look at the oxygens. We have 8 here, and we have also 9 coming from here, making it 17. So to make here 17, I have to write 17 over 2, meaning that this is going to be 8.5. But in the question, it is already said that we have to use whole numbers. So because of this whole numbers thing, it is going to be multiplied by 2. So this will be 2, this will be 17, this will be 16, and this will be 18. And when we sum those things up, we will get 53. This was a very easy question, right?
Yep.
Question number 2 is about finding the volume in decimeter cubes of carbon dioxide produced in this reaction. So again, would you be glad to solve this question for our followers after we get their answers?
Of course, yeah.
So we are giving 30 seconds because this is also an easy peasy question. Since it is at the beginning of the paper 1 exam, we have to be struggling, especially at the end of the exam, because they are getting harder and harder because the topics are getting wider.
Burak, can you let me annotate? So,
of course.
Let's be ready for it. Okay. I will choose red. It's my favorite color. All right. Is everyone ready? Burak, are you getting any answers from the chat?
Interestingly,
you can write your answers on the chat.
Yeah, please write your answers. Even if it is correct or wrong, please write them. And we have 6 viewers right now, and this is a great number.
Maybe you can ask your questions.
Yeah, if you have any questions regarding the topic. So if it is about the topic as well, we can also answer them, no problem.
Yeah.
We still do not have any answers, but 5 viewers. Maybe again you can start.
All right, let's do it. Okay, so what is the maximum volume in decimeter cube? And this is really important. We should underline this. Of carbon dioxide produced when 1 gram of calcium carbonate reacts with 20 centimeter cube of this concentration of hydrogen chloride. So here is the thing. It gives us the gram, the mass. So let's write this. In order to find the mole for this, then we should multiply it by 100 because it is giving us the molar mass. So we find that 0.01. So if this coefficient of it, it's 1, and we know that. So we can write it 0.01, and it's asking us about the where is it? Also the hydrogen chloride. So we can see that this is all it's. We can also multiply it with 2, and I'm writing divided by 1000 because it is asking us in decimeter cube, not centimeter cube. And when we do the calculations, then we find 0.04. What's happening?
Oops, sorry.
Okay.
Yep. Fine.
Okay. But we find that hydrogen chloride is in excess, so it is 0.02. We are finding 0.02 moles of hydrogen chloride is in excess. So let's not deal with that. And it's asking us about the maximum volume of carbon dioxide. So our coefficient is 1, and this coefficient is 1 too. So let's write 0.01. And it's asking a molar volume of gas. So we will just multiply this with times 22.7. And this one is equal to this one, so we find it C. So and I try to go step by step. So
again, first,
any questions?
Yeah. Do we have any questions, by the way? Yeah. Because Ege firstly detected that hydrogen chloride was in excess because when calcium carbonate was 0.01 mole, hydrogen chloride was 0.04 mole, where the coefficient ratio between them was 1 to 2. So we said directly that hydrogen chloride is definitely in excess. Therefore, we made our calculations according to calcium carbonate. It's a good question, right, again?
Yeah, and especially the part with excess.
Exactly.
You should be really careful about it.
So I think we can go with the next question now. Let me scroll down. 3. Which factors affect the molar volume of an ideal gas? 1. Pressure, 2. Temperature, and 3 is the empirical formula. Should I directly answer this or wait for any answers? Let's say 10 seconds. We give 10 seconds for this question. Any answers, guys, please? We have 5 viewers, and we are also very glad to hear that we have 5 people watching us right now for the preparation to mock exams. Should I go for it again?
Yeah, let's go for it.
Okay, so let's go for that. It says pressure. We know that an ideal gas equation is like PV is equal to nRT, where P pressure, V volume, and the moles, and R is the coefficient, and T is the temperature in kelvins. So we can see that pressure, we have the pressure, temperature, we also have the temperature. And third, empirical formula. No, it does not have anything to do with the volume, so we will directly go for 1 and 2 only. This is that easy. Perfect. Fourth question. Yes,
right.
It is also a common topic with physics HL topics.
Yeah, topic 7, particle physics.
By the way, physics students, please do not be concerned. It is coming very soon. It says, which electron transition emits radiation of the longest wavelengths? The words that we have to focus on in this question are emission and longest wavelengths. So we know that emission is releasing photons. So again, we have to directly reject answers such as B and D. Why? Because they're absorption. This is absorption. Let's write it. This is absorption. And then The second part is about longest wavelength. So as the wavelength increases, the frequency will decrease. Because imagine this. This is one wave and this is another wave, right? And we know that this is wavelength and this is also the wavelength. Do you see how frequency increases with the decrement in wavelength? So we know that it has to have the highest energy. The highest amount of energy has to be given. Therefore, when it says longest wavelength, it is asking for the weakest energy, smaller frequency. Therefore, we will go for C, definitely, right?
And also, Burak, I think we should let our viewers know what kind of wavelengths are emitted when it comes to 1.
Exactly.
Principal quantum number 1, 2, 3. When it is 1, it is UV light. When it is 2, it is visible light, and when it is 3, it is infrared. So, yeah, Lyman series. Yeah,
this is Lyman.
What I was trying to remember.
So, it means let me write it in this way. From n is equal to infinite to n is equal to 1, this is Lyman. And this is UV, like this. So when it is n infinity to n is equal to 2, we know that this is going to be Balmer, and this is visible light for sure. Do you see how the energy level is decreasing? And when it is from n infinity to n3, we call it Paschen series. Paschen. And this is infrareds. Yep, let's keep this in mind. Also for physics, it's important. Maybe the names do not appear in the IBDP for the chemistry section, but it might be useful in the following sections. So again, do you want to go for question number 5?
Yeah, let's do.
By the way, we don't have any answers. We still don't have any answers. Let me tell you about that.
Yeah, nobody's writing their answers.
Please, be participating. I think we can go for it again.
Okay, so it's asking X, Y, and Z represent successive elements, neon, sodium, and magnesium, but not necessarily in that order. What is the order of increasing atomic number? So when we remind ourselves of the periodic table, neon is here, sodium is here, and magnesium is here. So it is 10, proton number 11, and 12. Yes. So it is asking us about, and it also gave us the data for first ionization energy. So we know that when we remind ourselves of the valence electrons of these, then neon would be the hardest. Wait, let me write it. So neon is 2, 8, 8. This one is 2, 8, 8.
Neon is 2, 8, bro.
Sorry. Yeah, and this is 2 and 8, and 2. Yeah. So as we go across the periodic table, we know that the radius decreases. And if radius decreases, then ionization energy required to remove the electron from the last shell would be will require higher energy. So we know that magnesium, we don't know which place, but magnesium is the higher one than the sodium. Then neon would be the highest because it would it's the last electron does not want to move because they already have the octets. So X would be the highest one, neon. Then we already said magnesium would need more ionization energy. Then we said magnesium. And this is sodium. And what is the answer?
A.
A.
Yep.
I think I made a mistake here, Burak. Can you?
Let me see.
Can you help me?
I think it is perfectly fine. I think no mistake.
Yeah.
No
Yeah.
mistake.
Okay. Yeah. It's A. Okay.
Yep. So the answer should be A. And let me remind you about one thing. So as we are going down the like if we have periods, for example, we said like we were comparing sodium and magnesium. So there is such a thing that if this is the nucleus, for example, this will be 2 2 8 and one more, and so what is important here is that as we go from left to the right in our period, we know that moving from left to right in a period will decrease the atomic radii. So as Ege said, when the atomic radii is decreasing, obviously the element will say that I don't want to leave this electron, because we know that these electrons are closer to the nucleus because of the electrostatic attraction between the protons in the nucleus and those valency electrons. So they are closer. So when we go through the period from left to right, it will be more difficult to remove those electrons. So question number 6. Which property increases down group 1, the alkali metals? So this is directly a knowledge question. Let me tell you the answer. This will be absolutely atomic radius. Right, again?
Yes. And it is one of the easiest, but we should be careful still.
Yes, because let's remind our friends about those rules as well. So for electronegativity, we know that electronegativity, let me write, it increases.
And also, Mert Yılmaz also said that in the chat. He wants to, he's asking us about what happens to electronegativity, first ionization, or other features of the elements as we go across the groups and across the periods.
So as we
can make a summary.
Yeah, as we go across the periods, it increases. So from left to right, electronegativity will increase because we know that the nucleus is closer to the valency shells. So when we are at the very left of the periodic table, we know that the atomic radii is too large. So that when it makes a bond, covalent bond, it is much more difficult for this nucleus to reach the electrons in the bonds, so that it does not have that much electrostatic effect. But think about fluorine compared to like sodium. So it has a smaller atomic radii, so that nucleus is here, and it is much closer to the bonding electrons. Therefore, it pulls them more easily, which makes it more electronegative. And as we go up the periods, up the groups, it increases. It is again for the same situation. As you know, when we go from, if this is the periodic table, we know that going from left to right, radii decreases, and as we go here, radii increases. This down the group thing is because of new energy levels. We have new shells added to this. And the radii decrease is about electrostatic attraction between the nucleus and the valence electrons and the shielding electrons. Don't forget the term shielding electrons. This is very important for the DP exams. So about the first ionization energy, we said that there will be a decrease in the ionization energy, first ionization energy, as we go down the group, because we know that atomic radii is increasing, so the valence electrons are much more far away, much apart from the nucleus, so that they are already ready to go. They are saying that, okay, I'm not being pulled by the nucleus that much, so I can leave. A small amount of energy will be enough to leave it. And yes, this question was A, and we made a good summary about electronegativity as well. So question number 7. Again, should I go for it or you will go for it?
Yeah, another DP question that requires knowledge. But okay, let's give our friends maybe 10 seconds.
Yep. And by the way, you will be using the periodic table that is provided to you while solving this question. So
and actually, there's a trick here. And if our viewers want to see the periodic table, I will be showing them the trick there. You don't need to memorize. There is just a little trick. Okay, let's talk about it.
Yep.
Okay, so it says which element is a lanthanide. When I look at the periodic table, guys, and if you are looking at it as well, then let me say this. Wait a second, please.
If you want, I can open the periodic table.
Yeah. Please. I will be showing them that.
Just a second. So 1 second. Yeah, here. You have to see it in this format, but
yeah, IB loves those weird things, like putting the table like this.
So, okay,
bro. Can you let me annotate?
Yep.
Okay. So, guys, it's saying lanthanide. So, as you can see, we have two little periods here, and one is like this, and one is this. So, as you can see on the periodic table, you have lanthanide, 57 lanthanide, La. And lanthanides actually mean that the elements that we create in the lab, the elements that act like lanthanides, but actually are not lanthanides. So we can directly look for the elements that are in this part, because they act like lanthanides. And there's another thing, and this is called what was it called? The other part. It is TH, and as you can see, it is actinides. And you don't need to memorize this actually. Actinides, right? Yep. Yeah, you don't need to memorize this actually. You just have to remind yourself about this part. And this is the trick here. You don't need to memorize anything in IB. Yep. Just use your logic.
So we saw that it is terbium, right? Here.
Yes, it is TB because it is in this period. You don't need to memorize it, guys.
So let's go back to the question. So we said it is terbium.
Yes, exactly.
Question number 8 is now coming. Ammonia is a stronger ligand than water. And this is also given in data booklet for paper 2 questions. Which is correct when concentrated aqueous ammonia solution is added to dilute aqueous copper 2 sulfate solution. So let me directly tell you what is the important thing here. So first of all, our answer will be ammonia replaces water as a ligand, because stronger ligands replace weaker ligands. So our answer will be C, and you may realize that the other choices are not even related to the topic, because it says about color but ligand and color, but ammonia does not make a change in the color when it replaces water. There is a small splitting of the d orbitals. No, this is also wrong. The d orbitals in the copper split, this is also wrong. Yes, a good question, but it requires to be a little bit cautious. A little bit cautious. Because IB likes to give full structural formula with only structural formulas as well. So, should I explain it again?
Yeah, let's do it.
Okay, so you may say directly that, oh, there is 1, 2, 3 times 2, since it is asking for the bonding electron 6, you may say, but this is completely wrong, guys, because this structure is actually looking just like this. We have N, H, H. Please don't forget those H2N's here. So now let's count them. 1, 2, 3, 4, 5, 6, 7, and also 8. So 8 times 2 will be 16 electrons. By the way, please check if it is asking for bonds, sigma bonds, number of sigma bonds, number of pi bonds, or number of bonding electrons. This is very, very important. So we can proceed with the next question. Oh, this is question number 10. This is very important because we have the whisper theorem here. Whisper theorem, very, very important. Again, do you want to go for it or should I go for it?
Yeah, I can do it.
Okay, let me make it.
Actually, guys, there is a little trick here, and I will show you that.
You don't need to draw each and every little structure for this. Just imagine. Exactly. Just imagine.
Okay. Okay. So let's start. Okay, I will not start with A because it's in. If I was in the exam, I would not start with that because it looks a bit complicated. But let's start with B. Actually, this is the structural formula of benzene, and we know that in benzene, its structure is like this. By the way, 1, 2, 3, 4, 5, 6. Okay, so we know that it is H, 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 but in the benzene structure, we put this in order to show the delocalization of electrons. And this is actually resonance because we can write it in like this. Let me do it. Or like this. And this is actually delocalization. And we write the double bonds in different ways. Okay, so we eliminate this. Let's eliminate it. Let's come to C. In C, it is the structure of hexene. It is the structure formula. Let's write hexene, guys. C, C, C. And one more. Okay. H, 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 H. Okay, let's draw the thing here. Alright, this is the structure. But we can see that we cannot write this double bond in other places or here or here. If you write the double bond here, then it would be its isomer, not its resonance structure. And they are two completely different molecules. But in benzene, you can see that they are the same molecules, and there's delocalization of electrons. But in this part, there is no delocalization. So I would say C, but maybe Burak, we can do the D as well, ozone structure. Yeah?
Yep, sure.
Okay, so when we draw the ozone structure, we can draw its resonance structures like this. Sorry. I drew it wrong. Alright. Okay, so it is its resonance structure, and you have to remind yourself about this part. And the IB also likes to write it not like benzene, but C6H6. So be very careful about this part. Okay, I think that's all.
And do you want me to remind you about one more important thing?
Yeah, let's do it.
So, about this C6H12. So it has an isomer. This is for organic chemistry part, and for the organic chemistry part, it has a structure just like this. This is the isomer of what Ege just drew. And this is why we cannot just restate the position of double bonds, because it's not possible, just like Ege mentions. And another thing is that, let's talk about ozone a little bit. Ozone. Do we remember how to draw Lewis structures? Lewis structure. This is an important point for the IB because let's say we have O3, this is ozone. So while we are drawing the Lewis structure, let's remember that for the first step, we were just calculating the total number of valency electrons in our molecule. So since this is oxygen, oxygen has 6 valency electrons, and since there are 3 of them, we will say 6 times 3 is equal to 18. So second step, we will check how many electrons at how many electrons do our atoms become stable. So since this is octet rule, it will be 8 for oxygen. So 8 times 3 will give us 24. And let's do one more thing in the third step. In the third step, we will say that, so let's subtract 24 from 18 from 24, and we will find 6. This is the number of bonding electrons. So in the fourth step, we will say that 6 over 2 will be 3 bonds, since there are 2 electrons in each bond. And therefore, we can draw this structure just like this. O, 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 and this is here. Since we said we will have 3 bonds, and we will just show it in the structure of our Lewis dot structure, and as you can see, this will definitely have a resonance where we will have the double bond here, and yep, this will be the resonance. So ozone has definitely an resonance structure, and this is how we do it in the Lewis structure. It's interesting, right, again?
Yeah.
So we can now go for question number 11. Which metal has the strongest metallic bonds? This is an important point for the IB program. Will you go for it, or should I go for it again?
I can explain it.
Okay.
Okay, so it's asking which metal has the strongest metallic bond. Burak, can you let me annotate, please?
Oh, yes, sure, sorry. Yeah. Let me clear them.
Okay. So it says metallic bond. Let's remember what metallic bond is. It is the electrostatic structure. It is electrostatic structure between a sea of electrons and the metal cations. So if we remember this one, then we can easily solve this question, because when we take a look at those elements, we can see that it goes down the group. And Mert, this is the question that you want us to answer, and let's answer it. As we go down the group, then we know that its radius will increase. Let's write it. Radius will increase. And if radius increases, then what happens to the nucleus, the positively charged nucleus? Then we would know that, for example, for rubidium, let's say, we have this structure, okay, and this is the sea of electrons, then we would have less attraction here. But for lithium, and this is the structure for lithium, this is a sea of electrons. So there is less distance between them. So if there is less distance between them, then it would be the strongest metallic bond, because metallic bond is all about electrostatic structure, attraction. And also its melting point would be higher as well than the others. That's all.
Yep.
Any questions, guys? You can write it.
Yep, please.
Nobody's writing anything, but you can write it.
Do we have any questions, or shall we go with the next one? Any questions? Any? No? Okay, so question number 12. I am sure this is a topic that most of us forgot about, because this is the ozone destruction by CFC catalyzed destruction.
And Burak, let me be honest with you, I even forgot about this. I mean,
definitely, because there are too many equations regarding this problem. So, should I write all the required equations for this destruction? Global warming, it's coming, also warning for everybody. So we have 1, 2, 3, and 4 equations for this. And it is asking for only the first step. We are very lucky. We are very lucky. So let me write them. The first one is CFC in gas form is coming, and we will have free radicals, and free radicals in the atmosphere are usually dangerous. Let's not forget about it. And chlorine free radical as well. So this is the first one that is required from us. So we can directly say that our answer will be B, right? But do you want me to write the other equations as well again?
Yeah, I think we can write it.
Yeah, maybe we will be given.
Would be reminded of these equations, because they are very, like, they need some memory.
Definitely, definitely. And another free radical, and I have to remind you that this one over here is this, chlorine free radical is a catalyst, okay? This is a catalyst. So here we have ClO free radical plus oxygen free radical, and it will be oxygen plus chlorine free radical. So overall, the net reaction would be ozone plus oxygen free radical would produce 2 oxygens. And this is how it is working, right? Is everything fine?
Guys, if you need any questions, just
yes, please. By the way,
I think it's Burak, you perfectly explained it.
Thank you very much. By the way, you may ask in the second step why carbon-chlorine bond is breaking and not carbon-fluorine bond, because carbon-fluorine bond is much more stronger than carbon-chlorine bonds. So this is the reason about 2. So by the way, are there any specific questions that you would like to see? I'm asking to our followers, like from this topic or that topic, and if we have those questions, we can directly solve them. We can directly solve them if you want. Otherwise, it seems like we will end up with 40. So, it is asking, which statement is correct? We are in question number 13. And about this topic, I think a question may appear in the exam, because this is sigma and pi bonds. So, formation of sigma and pi bonds were also a minor topic, but an important topic. So should I also revise it again?
I mean, nobody's writing something, so I think we can revise it.
Very shortly, I will just define what a sigma.
Yeah, actually, it is very easy.
Yeah, very easy, by the way. Let me directly tell you the answer, by the way. Is it okay?
Yeah, let's do
it. It is C.
Why not?
Pi bonds are formed parallel to the axis between atoms. So I will draw sigma here and pi here, and let's write pi and let's write sigma here. So let's not forget that sigma bonds is an overlapping of s orbitals, pi orbitals, and the hybrid orbitals in different combinations. And we have to remember that this is a head-on overlapping. This is a head-on overlapping, meaning that if we have, for example, two s orbitals, just like, let's say, hydrogen for them, because hydrogen is s orbital, only an s orbital, and s orbital. This is the first case we may have for sigma bonds. Do you see how they head-on bang like this? And secondly, we may have another overlapping just in this way. Again, a pi bond is sigma bond is created here. A sigma bond was also created here. Again, a head-on overlapping. And the third case might be, it could be between an s and pi orbital as well, right? So this is P, this is S, S, pi, S, and P. So we have realized that there are three cases, or it could be hybridization, so more cases as well for sigma bond. And head-on overlapping, this is very important. And about the pi bonds, this is sideway overlapping. Sideway overlapping, and this can occur only between pi shape p and p orbitals. So p and p orbitals, let's say this is also a case, and this will be an sideway overlapping. Do you see sideway? It was head-on for sigma, and now for pi bonds we have sideway. So this is the bond axis, by the way. And what was the question asking? Pi bonds are formed parallel to the axis between atoms. Yes, we saw that it is parallel because it is sideway overlapping. It's good to remember all the information, right, Ege?
Yeah. And mini revision, better than IB's book.
Definitely, definitely. So question number 14. Ege, I think you can go for it.
Yeah, okay, let's do it. Okay, look, can you let me annotate, please?
Yes.
Okay, so here's the... Okay, I will clear it as well.
Now let me clear it for you.
Oh, okay, thanks.
No problem.
Okay, here is the most important thing of this topic 5, energetics part. As we can see, it's saying enthalpy on y-axis. Enthalpy means it is the energy from the vibrations and kinetic energy of molecules, and also potential energy as well. So it is the total internal energy of molecules. Let me write it because it is very important and it will help us answer this question. And it's for practice as well. So as we can see, reactants are in higher energy state than products. And if reactants are have higher energy than products, then we can say that it is less stable. And as we can see, the reactants are losing energy to the surroundings and become at lower energy state. So we can say that there is an energy given out to the surroundings, and this happens only in exothermic reactions. Then what is our answer? It says the reactants are less stable than the products. No, less stable, and the reaction is exothermic, so it is correct.
Yep.
It's A.
We are lucky we didn't have to read all of them.
Yeah.
So, by the way, you can keep this stability thing in mind. Like, if you are at the top of a chair, this is the example that our previous teacher used to give. If you are at the top of a chair, and if I push you, you will easily fall down because you are at a higher level, just like higher energy. But if you are like standing on your legs only, not on a chair, it will be more difficult to push you. Yep, let's clear it and continue. Thank you very much again, by the way.
Thank you.
So it is asking in 15, what can be deduced from the facts that ozone absorbs UV radiation in the region of 340 nanometers and molecular oxygen in the region of 242 nanometers? So let me tell you the answer. This is going to be D. The bonds between atoms in molecular oxygen needs more energy to break, because we know that 340 nanometers is a longer wavelength than the molecular oxygen destruction region, 242 nanometers. And we know that as the wavelength increases, frequency decreases, meaning that less energy. So it is already saying that we need more energy to break this bonds. This was all. This was all. The bonds in ozone are delocalized. How do we understand it even? I mean, the bond between atoms in molecular oxygen is double bonds. No. The bond between atoms in ozone are stronger than those in molecular oxygen. No, we do not have any idea about them. By the way, question number 16, this is directly like a physics or mathematics vector question, I have to say.
Yeah. But we have to be careful, and
we have to be careful.
And we should like remind ourselves of the enthalpy diagram here.
In those kind of questions, you have to think like, so if I am here and it is asking me to go from here to here, so how am I supposed to go from here to here as well?
Exactly.
We will reach the same point. We will reach definitely the same point. Again, do you want to do it?
Yeah, it is quite simple, but let's do it.
Yeah.
Okay. So, guys, we know that, as Burak said, we need to go from here to here, and it means that on the top I talked about the enthalpy diagram, and they have to be on the same energy level. They have to have the same enthalpy level. So we have to go from here to here too. So to go from here to here, all arrows must face the same direction as the lattice enthalpy diagram, because we want to go on the same level. So it is minus, but we need to have a plus to 361 in order to go up. So we make it minus 361 so that it is positive. Then we do the same thing for this, because it is positive and it's going up, and it's the same for this and it's going up, and also it is going up, so we just add them together. The only difference here is, as you can see in B, we put minus, so it becomes positive, so our answer is B.
Dear followers, be afraid of those kind of questions, especially in physics, Kirchhoff questions. It might look easy in chemistry HL, but in physics Kirchhoff problems, oh my god, they are like advanced level. So, which ion's hydration energy is the most exothermic? So, we can say that hydration is the amount of energy released when 1 mole of ion in gaseous state is converted into gas form. Sorry, aqueous form. Sorry. Amount of energy released when ions in gaseous states are converted into aqueous states. So this is a thing that we have to remember. So to be the most exothermic, we know that the magnitude of hydration enthalpy completely depends on the density of the ions. But the charge density. So charge density will increase when the atom is smaller. I wrote it capital, but it is smaller, definitely. So what is the smallest atom here? Sodium, no. Bromide, no. Iodide, no. Lithium, definitely lithium. Because it is only 1s2, 2s1. It is the smallest, right? Yep. This is all. Should I, by the way, or we have already done it. Yeah, okay. It says questions 18 are 19 are both about this equation. So again, maybe you can go for
let's
it.
do it.
Yep. Let me clear it for you.
Thank you.
You're
okay,
welcome.
so let's read the question, and we are given the equation here. Which change does not increase the initial rate of be careful about it, initial rate of reaction when calcium carbonate is added to excess hydrogen chloride. So, but you should be really careful about excess hydrogen chloride, but because it will be very important. Let's hear it. Okay, decrease in the size of the calcium carbonate particles. Yes, for initial reaction, rate of reaction, it would be quite important because when there is less amount of calcium carbonate at the beginning, then there would be less. I mean, there would be it would be less likely for hydrogen chloride and calcium carbonate ions to collide with each other. There is less probability because there is less calcium carbonate. So yeah, it would definitely impact. So A is not our answer. Increase in the temperature of the reaction mixture. Yes, it would firstly increase it because when they have more reaction, more temperature, then they would have more kinetic energy. And they have when they have more kinetic energy, then their activation and their energies would be higher. So when they collide, it would be there would be greater probability that these collisions have energy more than activation energy. So there will be more frequent collisions. So yes, it would definitely impact. An increase in the concentration of hydrogen chloride, keeping the same volume. Firstly, excess hydrogen chloride. I mean, increase in the concentration of hydrogen chloride, keeping the same volume. Actually, when we keep the same volume and when there's increase in the concentration, then let me write it because I want to show it in a clear way. We would have more molar of hydrogen chloride, but it is excess. I mean, it does not affect the initial rate of reaction. And for D, let's hear it. Increase in the volume of hydrogen chloride, keeping the same concentration. Let me write it again. No, because I want to show it. And decimeter cube. When we increase the volume of hydrogen chloride, then we would have to decrease the molarity of hydrogen chloride to have the same concentration. So yes, it would definitely impact. So I think it's the answer C.
Actually, the answer was D.
D.
Yeah.
I think I made a mistake here.
Let me tell you what the thing is here. So the thing is about when we increase the concentration by keeping the same volume, this means that there will be more particles per volume unit volume.
Yeah.
So
okay,
there will be
I
more
understood
collisions.
my mistake. Yeah, so when there's more hydrogen chloride molecules, then there will be again greater probability they collide.
Definitely.
I mean, excess here does not matter. I made a mistake here. I'm sorry. It would definitely impact, but this wouldn't, because there is no increase in the molar mass of hydrogen chloride here. I mean, there is no increase in their number of molecules.
So the initial number of successive collisions would be equal if the case was with the number d, because there will be same number of particles per unit volume.
Yes, exactly.
So next question. I like this question as far as I remember. Which methods can be used to monitor the progress of this reaction? This is a good question, everybody. And we will say change in color of this reaction mixture. Change in color of this reaction mixture? No, there is no color change. There is nothing to change the color with. Change in mass of this reaction mixture, it says. There will be a change in mass. And it is because of this carbon dioxide here. Look at its state. It is gaseous. So if we had it in a flask like this, it would go out. Carbon dioxide would go out. So it would decrease the mass. So definitely we have this. Change in volume of gas evolved. So if we were to keep it with a syringe, we would definitely be able to evolve it. So there will be a change in volume of gas evolved due to carbon dioxide, and our answer would be C. And here we have, which is true of an Arrhenius plot of ln k for the y-axis against 1 over t. So again, do you want to give the formula for this question, Arrhenius equation?
Yes, yes, and okay, I will annotate it. So guys, in question in the part 1 of the data booklet, you can see it. It is 16.2. Let me write it. And this is actually, and this will actually remind you of something we learned in mathematics. All right, this is the equation. Burak.
Yep.
I gave the equation.
Okay, so the graph does go through the origin. This cannot be true because we have ln A here. ln A, oops, sorry, I was in my own thing. ln A. So it cannot go through the origin. The activation energy can be determined from the gradients. Yes, of course we can do it. Do you know why? Because if we were to plot it against 1 over t and ln k, we already have ln k here, and this is the 1 over t. So negative, enthalpy over R would give us, this would be our m, meaning the gradients. And since R is a constant, multiplying it by negative R would give us our activation energy. So this is that much easy. So C, the intercept on the x-axis is the activation energy. No, because we have to put 0, but then we will have also the problem about ln A once again. We have ln A here. The intercept on the y-axis is the frequency factor A. No, this is also wrong because we again put 0 and we find it again not the answer given in D. So our answer has to be B. Good question in commenting about formula. Good use of the formula booklet will bring a lot of benefits for you. Okay. 21. Which is correct about reaction mechanisms, it is asking. So, for this question, a species that is zero order does not take part in the reaction. No, it just does not have any, its concentration does not have an impact on the reaction expression, reactions rate expression. But it does take place. Think about like SN1 mechanisms. Hydroxide was in the reaction, but it was just not having an impact on the rate expression. A catalyst does not take part in the reaction. No, it does take part in the reaction. Let's define a catalyst. So for a catalyst, we say that lowers activation energy. This is the first point. without being used up a different pathway. Those are usually transition metals which lowers the activation energy without being used up to create another pathway for the reaction. But please don't forget that increases rate of forward and backward reaction. This is very important. So a catalyst does not increase the rate of a reaction because it increases both forward and backward reaction rate so that they will be still equal. This is like walking backwards on an escalator, right? But you see, reactants in a fast step before the slow step are included in the rate expression. Definitely, this is correct. Reactants in a fast step before the slow step are included in the rate expression. This is correct. We talked about this in SN1 and SN2 mechanisms previously yesterday. So the reactants in fast step after the slow step are included in the rate expression. This is wrong. They are not included. They are not included. 22. Which variable affects the equilibrium constant? Again, do you want to explain why this question is D?
Yes, of course. Okay, so we need to know a little bit about equilibrium. So in equilibrium constant, we said it is the concentration, and we express concentration like this: concentration of products over reactants. And if there are more than one product or reactants, then we write them separately in brackets, in these square brackets. Okay, let's see. It says atmospheric pressure. So in an equilibrium for gases, the equilibrium constant would be constant, because if we increase the pressure on reactant side, then it would always come back to its equilibrium position again. So the ratio of these products and reactants would always be the same. So Kc would always be the same. So no. For catalyst only decrease the rate of forward and backward reaction. It does not have any impact on the concentration of products or reactants. So no way, no, it's not B. For C, it says concentration of reactants. So if we increase the concentration of reactants, then equilibrium would shift to right. But at the end, it would actually come back to its equilibrium position again. It would actually shift to right, and then it would come back to its position again. So the ratio of these products and reactants would always be the same again. So it's not true as well. But for temperature, yes.
And we have it also in Arrhenius equation, right?
Yes, yes. Actually, I was going to talk about that, and we can prove it with Arrhenius equation. I think that's all. I mean, if anyone has any question, you can ask it in the chats.
We have 3 followers who are following us from the beginning. We thank them a lot. But if they have any questions, please use the chat section. We are always here. So it is saying about question 23. Components X and Y are mixed together and allowed to reach equilibrium. The concentrations of X, Y, W, and Z in the equilibrium mixture are 4, 1, 4, and 2 moles per decimeter cube respectively. What is the value of equilibrium constants? So, for this question, Ege, do you want to go or do you want me to go?
I can do it.
Okay.
Okay. So as I said in earlier question, the last question, we said that it is products over reactants. So let's write it. But we need to be careful about these coefficients. I forgot to talk about it. It was not relevant, but it's relevant now. For reactants, products, let's look at that. W and Z. For W, we have the coefficient 2. So we are going to write it by this way. Times Z. Z has coefficient of 1, so it is 1. We don't need to write 1 here, but I want to show it. For Y, it has coefficient of 2. So we write the 2. And times X. And let me write 1, just for making it clear. So it already gave us these concentrations. And be careful about it. This is the expression for concentration. But if it gave us any information about mole and volume separately, then we would have to find their concentration. And this is the biggest mistake I made when I was trying to learn equilibrium. So let's write them. It already gave us these. For X, it is, let me write it. For X, it is a 4. Okay, let's write 4 here. For Y, it is 1 over to the power of 2. So it is already 1. For W, it is 4. But we have to write it in to the power of 2. And for Z, it is 2. But for Z, it is in the power of 1. So let's write it. So 16 times 2 over 4. And we are finding 8 here. So the answer is D. If you have any questions, you can ask it right away.
So again, after this point, do you want to go with the selected questions?
Yeah, let's do it.
Now let's have a look at it. We will go for chemistry. We will go for paper 1 review again. So here I have some questions for you, everybody. I hope this is the correct one, right? Let me see, please.
Yeah.
Yes, this is the correct one.
True.
Yeah. So again, do you remember the question that you sent me on WhatsApp previously? Shall we go for it?
Oh my God!
Okay.
What a question it was.
Let me explain it. Let me explain it. We had to think a lot. Yeah. Okay, so
it's about organic chemistry, and if you did not watch Burak's review, then you can watch it.
So I found it.
It was quite helpful for me.
So, do you want me to explain it?
Yeah.
Let me go for it. So, question number 20. Which statement is correct? Okay, so let's remember one thing, please. As I will write it in red, SN1 and SN2. Just as you may remember, in SN1 reactions, since this was a first order reaction, we did not have the impact of hydroxide, concentration of hydroxide in our rate expression. And it was only, rate was K times halogen alkane. Right? And for SN2 reactions, we had the impact of both rate is equal to K times OH minus and halogen alkane. Did we remember that? Yes. So it is saying that the rate expression is rate is equal to K times C4H9BrOH minus. So you may ask, oh, how are we going to answer this question? You have to check the impact of changing the initial concentration on the initial rate of reaction. So let's have a look at it. Let's see if C4H9Br concentration is effective on the rate expression. We have to keep OH constant in this case. Let's keep OH constant. And this is going to be doubled, x2, from 0.02 to 0.04. When we doubled it, let's see, initial rate is also doubled. So this means that this part is correct. K is also correct, we say. But let's have a look at OH. So in this section, I have to keep the concentration of halogen-alkane constants, 0.04. And let's have a look at what happens when the OH concentration is doubled from 0.02 to 0.04. What happens when we doubled it? It remained constant, no change. So did we realize that OH should not be here? Because this is SN1 reaction. This is SN1 reaction. For those of you who are careful, you already realize that the answer would be SN1 mechanism, D. But it says the rate increases by a factor of 4 when the OH is doubled. For such a case, OH has to be a second order. It has to have the coefficient of 2, just as Ege explained previously. So when we have a look at it, when OH is doubled from 0.02 to 0.04, we see that there is even no change. Hani bırakın 4 katına çıkmayın, no change. So A is wrong, B is wrong. It says C4H9Br is a primary halogen alkane. So this is a fun discussion we had with Ege, because we were saying like it says C4H9Br, so Br is at the very end, so it should be, we were saying like it should be primary halogen alkane, but we forgot about one thing. IB wants us to find whether if it is primary or tertiary, right again? So this is tertiary halogen alkane, since it is SN1 mechanism.
It is the combination of more than 2 topics, actually 3 topics.
Definitely. By the way, I have to ask our followers, do you want us to go with more topics? We will solve a few more questions, just a few more questions. Do you want us to go with organic chemistry questions, organic chemistry paper 1 questions, or do you want us to go with variety of topics? Could you please write it? Could you please answer this question? This is very important for us, because we would like to be focusing on the questions that we are struggling. Do we have any answers for our followers, viewers? By the way, Ege, I forgot to take my water with me.
Okay.
I'm a little bit obstacling from the growth of my throat. Literally. By the way, good try. Again, no answer, please. Organic chemistry questions, or do you want questions from all topics? Range of topics, please answer it. Please, somebody. Nobody?
3 viewers. But...
Yeah, we have 3 viewers. We reached at sometimes 7 viewers, by the way. This is a huge compliment for our channel, I have to say.
I think they made a deal on not talking, so I think we can go for variety of questions.
Variety of questions? Alright, let's go for them. So, okay, again, rate. Let's make it the last rate question, because I believe there will be a question about rates.
Enough of them.
Yeah, enough of them, literally enough of them. So, again, for rate, we know that rate is shown by 1 over s, right? Per seconds. Per seconds.
Yeah.
So, meaning that this is s negative 1. Okay, so for here, this is a second order and this is a first order. So let's multiply them. It would be a case like, since both x and y are shown in moles per decimeter cube, square times mole decimeter cube, right? So when we square this, mole square over decimeter to the power negative 6 times mole decimeter cubed, right? Yeah.
Exactly.
Yes. Right.
Actually, we solved this question now.
Yeah.
It is much easier to.
It is much more easier for us. So, at this point, we will have to just cancel them out to get only per second, so that we will go for the answer of D, right?
Yes. And,
Yeah.
and guys, when you see square brackets, then always remember operate.
Should I go to the next question?
Yeah, let's do it.
Let me scroll it down. Let me see what else we had in the questions. Okay. Let's give Gibbs energy. What do you think about that?
Oh yeah, we never solved the question about Gibbs energy.
Definitely. So
all right.
Let me just do this. Okay, Ege, can you do it?
Yes,
okay.
I can do it. Okay, guys, we have the equation for this actually. And let's give the equation, and I'm looking at this equation from the data booklet that is given by the IB. Okay, so this is Gibbs free energy. Gibbs free energy. I won't write the whole thing. This is enthalpy, change in enthalpy, and this is the change in entropy. This is very important. Instead of writing these ones, they could have written it with their names, not their symbols. We should learn it. So it says which combination of enthalpy change and change in entropy will result in a non-spontaneous reaction at all temperatures. So non-spontaneous means that our Gibbs free energy have to be positive. I will write it. Maybe you can take a screenshot and take it as a note. Gibbs free energy is always positive. Always. For negative, it is spontaneous. Okay, let's take a look at it. Let's take a look at these ones that make it always positive. So if you want to be positive, then this should be always positive. Change in enthalpy has to be always positive. But for change in entropy, we have the negative sign here, and be careful about it. And if we want to make this Gibbs free energy always positive, then we should have positive here as well. So if we multiply it with -1 and change in entropy, we should have positive. So it is negative, so that it is positive here. So it is A. And that's all. That's all we need to solve this question.
By the way, I have to remind our followers about one more thing. Not about this question, but do you have anything to say about this question?
No.
Okay. So I forgot to say one thing about the previous question we solved. Like we said, this is per second, but this is like this is moles per decimeters per second. So we know that they are going to, if you would like to have an equation just like this, this is the rate, this is the rate. So we have to cancel this one and only this part of it, and we have the k here, okay, k here. So k should be such a canceling constant that it should have such a unit that only 1 over s should be left on the other side. So we are just writing the opposite of what is here. So k has to be 1 over mole square decimeter square, just like this, and times second, because we have the second here. So I took this second here, and as you can see now our answer will compromise. Mole -2 decimeter 6 s -1, right? Yes. This is how you should do it. I forgot to say the other part of rate. Pardon me for this. Yep. Oh, Ege, now do you remember how we talked about catalysts?
Yeah.
I said there could be questions about it. I said it. Yeah. And now it is coming.
IB is trying to be tricky, but our viewers will not fall for their
Definitely, definitely. So let's have a look at it. Which changes shift the position of equilibrium to the right? So the rate of forward reaction should increase, but the rate of backward reaction should not change or decrease. Let's have a look at it. Increasing the temperature. This is, let's see. It says plus 58 kilojoules per mole. So isn't it endothermic? And let's remind it, delta H is greater than 0 when this is endothermic. And in endothermic reactions, think about it in this way. A reaction happens when you are exerting heat, it is happening. But in exothermic reactions, exothermic versus endothermic, so delta H is smaller than 0 in exothermic, and delta H is greater than 0 in endothermic. So we know that Le Chatelier's principle is a principle of action and reaction. So let's think about it in this way. It says increasing the temperature. So when we increase the temperature, the reaction will say that, oh, I have to grab this energy from my endothermic side to ensure that I am decreasing the temperature back into its original level. The reaction is trying to stay stable. This is the law of the nature, inertia. You have to continue what you are doing, just as if you are braking. You will go forwards. You are accelerating, you will go backwards. The reactions are the same. If you are exerting heat, it will absorb it through its endothermic reaction to lower the temperature. So we understand that since the forward reaction is given as endothermic, this will definitely favor the shift of equilibrium to the right. Decreasing the pressure, it is about moles. When we again decrease the pressure, it will say that, oh, I have to have more moles of gas molecules to increase the pressure. Again, inertia. So when we lower the pressure, when pressure is lowered, moles of, let's say, A gaseous increases. So this will also happen because we have only 1 mole of gas. By the way, please be cautious about the states G. Sometimes they give liquids, solids, you know, right? Aqueous. Be careful about the states, gases. So this has 2 moles, and as we decrease the temperature, it will increase from 1 mole to 2 moles. But adding a catalyst, as I said before, it increases the rate of both forward and backward reaction. So there will not be a shift. No, no. So it will be only 1 and 2. Perfect, perfect. Ege, do you want to see some more advanced organic chemistry questions? Since this is the last topic that we covered. Let's go for it.
Let's do it.
Actually, not all of them are like advanced, I have to say, just like this one. Ege, can you go for it, maybe? Let me just let you annotate.
Yeah, let's do it. Okay. I was holding my pen. Okay. So, which equations represent the incomplete combustion of methane? So, incomplete combustion means that there is not enough oxygen in the reaction, and also as a product of these incomplete combustion, we need to have carbon monoxide or just carbon itself. But when we have complete combustion, then we always have carbon dioxide, and this is the thing we should remember. So when we look at the products, as you can see, we have 2, and this is correct because we have carbon monoxide as the product. And if you look at 1, let's look at 1. This is methane, and it reacts with 2 oxygen, and there's actually plenty of oxygen if you look at the coefficients. And the product is carbon dioxide, so no way. And when we take a look at 3, then we have the product as carbon. So yeah, it is also incomplete combustion. I think the answer should be C.
Definitely. So insufficient amount of oxygen. And you know, again, in Turkey, this is a great problem, right? Like,
Yes, exactly.
because of carbon monoxide poisoning, lots of problems and lots
In
of
winter
accidents.
especially.
Yes, in winter, lots of accidents in Turkey happened, and it hurts a lot. Yeah. Which statements about substitution reactions are correct? It says the reaction between sodium hydroxide and 1-chloropentane predominantly follows SN2 mechanisms. Let me draw 1-chloropentane for you. 1-chloropentane. Okay. It will be 1, 2, 3, 4, and 5. So since it says 1-chloro, let's draw it from this side. Ding, ding. Those are hydrogens, by the way. I'm writing them so fast, so so as you can see, as we talked previously in yesterday's session, we said that the carbon which carries the functional group chlorohalogen, if it has 2 hydrogens bonded to it, this is primary halogen alkane. And what did we say yesterday? Primary halogen alkanes follow SN2 mechanisms, whereas tertiary halogen alkanes follow SN1 mechanisms. So this one is definitely correct. We said the reaction between sodium hydroxide and 2-chloro 2-methyl predominantly follows an SN2 mechanisms. We don't even need to draw this. 2-chloro 2-methyl butane. This is not a primary halogen alkane, so it cannot predominantly follow it. Wrong. The reaction of sodium hydroxide with 1-chloropentane occurs at a slower rate than with 1-bromopentane. This is correct. This is definitely correct because this says 1-chloropentane occurs at a slower rate than with 1-bromopentane. Chloro is a better leaving group than bromo. Please remember that increasing ionic radii makes it a better leaving group. Just like iodides, it is even better than bromides. So we said 3 is also correct, so our answer would be B. Again, shall we go for last 2 questions? What do you think about this? Or
Yes.
is there anybody who insists in the chat that we should go with the questions? If you think we should go more with the questions, we can go for it because we have lots of questions that can be solved.
I think they made a deal on not talking on the chat. I'm quite sure of it.
Possibly. If you think we should go more with the questions, please write it on chat that go more with the questions. Okay, again, let me make you annotate. Yes.
All right. So it says identify the functional group present in this structure formula. So I think we should firstly write draw the structure here. So it says COCH2CH3. Okay, let's try to write it. I mean, C. Okay, we can write it. And when you are writing these equations, just be careful. Carbon needs to have 4 bonds. And be careful about it, and it will make your lives easier when you are trying to draw the structure formula. And it says CH2, so I think we are getting it right.
Again, let me tell you one thing.
No, I realized I made a mistake. Alright. Okay, guys. When you are trying to draw, guys, just try to experiment with it. I just realized my mistake, and I will tell you about it. H and O.
definitely.
No. Yeah, you
Yep.
can also write it by this way, right? Or H here, doesn't matter. So actually this is the functional group of this compound. And when we have this functional group at the end, then this is the aldehyde. And most of my friends, and I used to do it, most of my friends confuse it with ketone. But ketone is this. This is the radical part. It doesn't matter. It is in, let's say it is carbon. Let's not write R. It is C. This is ketone, but we have this at the end. So it is aldehyde. Yeah, I think it's, yeah.
Definitely. So it is asking for the IUA, I will say IPAC, name of compound this. It's usually like this long. So please, when you see this COO, you don't need to draw this. We talked about this in our previous session. Divide it from, let me take the red pen, from O. The part with CO will be your carboxylic acids. And this part will be your alcohol. So what did we say? Add O8 for your carboxylic acid and EL for your alcohol group. So let's have a look at it. Carbon, how many carbons are there? 1, 2, and 3. This means prop. Actually propan. And then we will add the O8 part, making it propanoate. And from here we have, let's see, 1 and 2 carbons. So this will be ethyl. So this is ethyl propanoate, right? Just use this trick, divide it from the O, and the part with the CO will be your carboxylic acid. We are adding the suffix of O8, and for the other part this will be your alcohol, and just add "-il", like methyl, ethyl, propyl, those kind of things. Which statements? Enantiomers. Again, enantiomers.
I hate this.
Yeah.
All right.
I mean, this was at a part of the course where we were really sick of listening, literally. I mean, because it was like, okay, last one thing is left, just a small concept, one small thing. Oh my gosh, I'm looking at it, optical isomers, chiral compounds, racemic mixtures, distinguishing between them. I was like going literally crazy with Ege on
God.
Zoom's chat session. This was literally crazy for us. And then, which statement is correct about enantiomers of a chiral compound? So we can directly understand that their physical properties are different. No, their physical properties are the same, but their chemical properties are similar. All their chemical reactions are identical, not identical. A racemic mixture will rotate the plane of polarized light. A racemic mixture will definitely rotate the plane of a polarized light, but in opposite directions. We talked about this before. In different. One goes this way, another one goes this way, because they have different polarization properties. So, again, maybe you can go for it, right?
Okay.
It says how many structural isomers exist with the formula C3H5Cl3. So the answer is already 5. So maybe you can draw them.
Okay.
Yep.
Let's draw it. Okay. The first thing. See. Guys, we should, I think, try to draw firstly the
why don't we draw the skeletal formula so that our friends will understand that in the exam they can also use skeletal formula?
I'm not good at skeletal formula.
Really? Okay. So once you draw it, I will just draw it.
Okay. H. And we have CL, CL, and CL here. Okay. So we have 5 of them. And let's try to write these isomers. And it's saying structural isomers. Okay, so one is here. Let's try to draw here. C, 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 and maybe we can try to draw it here, because instead of writing 1, 1, I mean when we are writing its name, it will be 1, 1, 1, 3 chloro, but here 1, 1, 2, 3 chloro. It will be a different structure. And if I will not draw all of them, but I wanted you to see it. So we can actually write it also by this way: 1, 2, 1. 1, 2, 2. Let me write it, guys. CL, CL, and CL here as well. And this is the third one. And what is the fourth one? Burak, can you say it?
It is going to be 113. 113 3-chloropropane, and the last one is obviously 123 3-chloropropane.
Exactly. And we will just try to rotate them again. C.
Just make sure that you are obtaining different structures, by the way, because this has 3 carbons. So putting, let's say, 1, 2, 3 carbon. If you bond 2 carbons to this one and 1 chloro to here, this is one structure. But if you make it like 2, 1, this is also the same structure, because it is again 1, 1, 2, 3 chloropropane. Okay? Make sure that you are having different structures. So think symmetrically while drawing them. So do you want me to use skeletal formula again?
Yeah, let's learn it.
Okay.
Let's learn it. When our teachers were explaining us, I mean, I didn't pay quite much attention because I thought I could write it by drawing them, but I think skeletal formula is much easier. I can realize it now.
So about skeletal formula, this is propane, by the way. Each corner represents 1 carbon. So what are we going to do? Chloro, chloro, chloro. This is what? This was 1, 1, 1, 3 chloro propane. Let's go with the second one. So the second one would be 1, 1, 2, 3 chloro. Sorry, 1, 1, 2, 3 chloro. Yes, I said it correct, right? Yeah. So let's draw it just like this. So since we said 1, 1, and we will bind it to the second one, chloro. So this was 1, 1, 2, 3 chloro propane. I will not write the names of the other ones, but just mention about them. So the next one would be just like this, and we would have 1, 2, 2 chloro, 1, 1, 2, 3 chloropropane. It is a little bit long, sorry. And then last, fourth of all, we will have this structure where we will have 1, 1, 3 chloropropane, and then as the last one we will be writing 1, 2, 3 chloropropane. So it will be just like chloro, chloro, chloro. So it is much easier to think symmetrically, by the way, and it doesn't consume that much time, right?
Yeah, and we saved a lot of time.
Yeah, we saved a lot of time
by using skeletal formula.
So you may also use them. So this was all for my organic chemistry reactions, I guess. And we said C for this one, right? Yeah. Still solving questions. So again, do you think we should end our live session here? We
Yes,
asked our followers, we asked our viewers, but we didn't get a response. But still they are watching. 2 followers. Actually, they were 3 just a second ago. We thanked a lot of. We thank a lot to them. I forgot speaking after this long session. So, do you think we should stop here?
Yeah, I think we should. We can maybe continue in our next session.
So, by the way, this is a message to Bilkent Erzurum Laboratory School people. So, since it will be a 60 minutes long mock exam and it will be made on Google Forms. So, actually, while Ege and I were discussing about the possible questions, potential questions, we said that it is not likely to have a drawing question in paper 2 section, and it will be a majority of paper 1 questions. So what I suggest you do is that you may now solve questions, solve one paper 1 on your own after this live session, and then have a look at the chapters. For example, if you have the exam preparation guide just like this, just go through them, have a look at the topics for possible paper 2 questions. And what we suggest as felsefesinde team is that there might be a question about acids and bases in paper 2, because it is about calculation, and this is one of the very last topics that we have covered so far. So we might have a question, and we were also saying again which topic could come.
I mean, we talked about like mostly organic chemistry questions could come for paper 1. So guys, I think it will be mostly based on knowledge questions, not on commenting questions that requires like reasoning for paper 1.
Definitely.
We cannot draw on paper 2 because it is Google Forms, right?
Yeah.
And I think we said energetics, like
energetics,
right?
Yes.
Enthalpy change that does not require much calculation, and we can easily write them. We can. I think our viewers should take a look at energetics topic 5 and its HL part if they are HL.
Definitely. And for SL people, actually for SL, I do not have many suggestions, and I actually don't know which of the questions that we have solved were also applicable for SL students. But I think it's always good to know more, right? So I think this might be the end of our session for now, right?
Yeah.
So we thank you a lot. Please make sure that your calculators are charged well for tomorrow's and other sessions. We will continue having live videos like that with you, in which we are either revising chapters or solving past paper questions. So please follow up. And for 11th graders, I am going to make a live video about mechanics as soon as possible, because also my physics exam is approaching. So please follow up. Stay healthy, take care. And again, do you want to add anything more?
I just want to thank them for listening to us, and I'm actually a bit angry about those 3 people because they made a deal on not talking on chat.
No. But again, they were here all the time. We thank them a lot. I mean.
Okay, thank you guys. I'm just kidding.
You were always here, and good luck in your exams. Special good lucks to those 3 people who were consistent about staying in our live video and watching us. Thank you very much for following. I hope it helps. And yes, good luck. Yeah.
Good luck, guys. Take care.
Bye bye.